Hello, everyone. Welcome to our discussion of the Hubble Law for Science 121 here at Luther College. I'm Professor Jeff Wilkerson. What we're going to talk about here today in this very short video, for those of us in class on Friday, we're looking at slide 10. I think it is. Let me make sure that's the right number. Yeah, this video is entirely focused on slide 10. And so what we're going to do is we're going to look at this Hubble law. Recall our earlier discussion about how several of the first Doppler shifts measured for galaxies. Those galaxies were blue shifted; they were coming toward us. But we're just talking about a handful. We're talking about a few, but a few out of 10 or 15 is a reasonable enough fraction. But by the time we had measured 100 or 200 Doppler shifts for galaxies, there were still just a few that were coming toward us, and nearly all of them were moving away from us, and many of them moving away from us at extraordinary speeds. And so we realized that the rule was that galaxies were receding from us. And we will talk more about this as a bedrock piece of evidence for the Big Bang model on Monday. But we want to use this idea that the galaxies that are receding from us, not just chaotically. So the key part of the Hubble law is that galaxies that are further away from us are receding more quickly. And in fact, it's a linear relationship, not a squared relationship, not a logarithmic, exponential, or any other kind of mathematical relationship, but a linear relationship. And that's going to become really key for us on Monday. But for now, let's just work with this idea that the Hubble law looks something like this. It says the velocity of recession of a galaxy from us, as determined by the redshift, by the Doppler shift. Remember, V over C is equal to delta lambda over lambda. That's our approximation of the Doppler shift, wavelength shift that we looked at. Remember the lab we looked at with Arcturus and the Earth in orbit, and that's the shift in the wavelength. That's the unshifted rest wavelength. That's the speed of light. And this only works if the velocity is relatively small relative to the speed of light. Otherwise, we have to use a more complex relationship. And as it turns out, with the recession of galaxies, that case is often not met. The speed can be a significant fraction of the speed of light, the speed with which a galaxy appears to be receding from us. But it looks something like this. This is the distance, and we'll often write the distance in megaparsecs, and we'll write the velocity in kilometers per second. And the data can be very well fit with a line. So it's a linear relationship between the distance and the velocity, not a parabolic, not an x squared relationship or something like that. It's this linear relationship that we will write the Hubble law as the velocity of recession is equal to the Hubble constant times the distance. We put a sub-zero on the Hubble constant, and now that we're working with history of the universe, what we're talking about with a sub-zero means as measured today. So anything that has a sub-zero on it means the Hubble constant, for example, in this case, the Hubble constant as measured today. And so we call it a constant because it's a constant in space, not a constant in time. So it's a constant. Right at this moment, if we were to make measurements all across the universe, we should get the same Hubble constant. But if we go back 1 billion years or go forward 8 billion years or whatever we do, we should get a different Hubble constant. So that means as measured right now, and it means constant in space, not constant in time. This is what can and will be varying over time. And so this, now, the way we're going to use it a lot of the times is to actually measure the distance to distant galaxies. This now becomes one of our last steps of measuring distance in the universe. If we know the Hubble constant, which is just the slope of that line, right? That's just the slope of that line on this graph. If we can measure that slope and we know the Hubble constant, then we will then be able to use this relationship. We just measure the velocity with our Doppler shift equation, and we can measure the distance to a distant galaxy. Distance is equal to v over h naught. And in fact, when you read distances to far off galaxies, this is the number one way these are determined. Not the only way, but the number one way. Now, as we get down here, close nearby, it's not a good measure of distance because those first galaxies that we saw that were coming toward us, those galaxies that were blue shifted are very nearby galaxies. And so, we're all in orbit around our local gravitational center in our local group of galaxies. And so we're orbiting around there. So some of these are coming very close to us. And as we get out here, for example, suppose there's a cluster of galaxies out here. And as we get out here in this cluster of galaxies, that cluster of galaxies is all orbiting, all the galaxies within that cluster orbiting around the center of mass of that cluster. And so you have the Hubble expansion, as we'll talk about on Monday, pushing that galaxy away from us. But at the same time, think of it like a swarm of bees. You got a swarm of bees that's moving away from you, but within that swarm, the bees are all buzzing around, and so some of them are coming towards you and some of them are moving away from you. And so you have two different velocities. You've got the velocity of the swarm moving away from you and the velocity of the individual bees within the swarm, and you add those together. Very near us, because the velocity of the swarm or the velocity of the cluster of galaxies gets to be greater the further away it gets. The individual bee velocity in there, the individual galaxy velocity within there cannot overcome the recession. And by the time you get out here at great distances, you really only see that recession velocity. You can, the way you want to find that is you want to look at a cluster. You got 20 galaxies or 30 galaxies. Take the average velocity of all of them. Some of them will be coming towards you, some of them will be moving away from you. You average it out and you're going to get the velocity of the swarm, the velocity of the cluster away from you. Very near us, the velocity of the cluster, the velocity of the swarm of bees is very small. So when you're very near us, the individual velocities of the bees can overcome the swarm velocity, and you'll see some of them moving toward you. But by the time you get out here, not very far at all, you don't see many. You don't see many bees in many galaxies. You don't see any galaxies coming towards you because that swarm, that cluster velocity is so great that the individual galaxies cannot overcome it. So that's what we see going on out there. And so, for my time, for the time that I've been around working in astronomy, there's been a lot of effort to try to measure this constant, this Hubble constant, the slope of this line. And it sort of bounced early on. When I first went to college, it was bouncing around between 50 kilometers per second 50 kilometers per second per megaparsec. So for every megaparsec distant, the galaxy cluster was moving 50 kilometers per second faster. A megaparsec is a million parsecs, right? And so it was bouncing between 50 and 100, 50 and 100, 50 and 100, 50 and 100. And it's settled sort of in the middle of there over the last few decades. And interestingly enough, there are sort of two ways to measure this, and we won't go into these right here. There's sort of astronomical approaches to measuring the Hubble constant, and there are what we would call cosmological approaches to measuring the Hubble constant, thinking about space writ large and the history of the universe that we'll talk about on Monday. That's cosmology. That's talking about the entirety of space and time of the universe and what its history is and what its future is. And so we will discuss that on Monday. And so there are approaches associated with thinking about that would give you the Hubble constant. There are astronomical approaches that would be using, for example, measuring the distance to these clusters using Cepheid variable stars or some other measure like that, and finding the distance and then finding the recession velocity and making a graph just like that. Those would be astronomical approaches. Okay? And so, interestingly enough, there are more astronomical approaches to measuring this Hubble constant, but the astronomical approaches nowadays settle pretty close to about 74 kilometers per second per megaparsec for h naught. The cosmological approaches settle at about 67 kilometers per second per megaparsec. Probably the best measure is 70. Last time I looked at this, these change all the time as people do analysis, but the last time I looked at this was 74.4, and this was 67.4. So somewhere between 67 and 68, 74 and 75. And these numbers were known with sufficient precision that they're incompatible with one another. So there's some sort of thing going on in the measurements that we don't understand, that we don't know which one of these is right, or if they're both wrong, and the answer is something different. But we know that they're not actually statistically compatible with one another. So for our purposes, we're going to take something in the middle right there, probably, I don't care. when you're doing calculations, I don't actually care if you want to use 67, use 67. You want to use 74, use 74. But I'm going to say for ease of use, let's just use 70 kilometers per second per megaparsec. Okay? I think your book, if I remember correctly, your book, my edition of your book, I haven't seen your new edition of the book, use 72 kilometers per second per megaparsec. But let's use that 70 to stick in here, and then we can say the velocity divided by the speed of light, delta lambda over lambda, get the velocity, stick that in here, divide by 70 kilometers per second per megaparsec. The kilometers per second is going to divide out and cancel the kilometers per second. You're going to get a distance in megaparsecs. So that's exactly how we're going to want to use this sort of Hubble law. And I'm going to grab your lab book here and look at the lab that we would do next week, but I don't think we're going to do the lab next week. I think we'll just work on projects again. And the lab that we were scheduled to do is actually working with this Hubble law. And I think it's about lab 14. I'm going to find it in here. It's in the section on measuring distances in the universe, because that's what we're going to do. Yep, it is lab 14. So lab 14 here, and you'll see what we would have done in this lab. So if you look at your lab, what we would have done is we would have graphed the distance to these clusters of galaxies and the recession velocities. So the recession velocities would have just been measured, determined using the v is equal to c delta lambda over lambda. And the distances would have been determined different ways. And you can see some of the ways in table 1 there that we measured the distances to these galaxies. So you could use Cepheid variable stars, good out to about 30 megaparsecs. But if you can't get further than that, you have to start using like type 1a supernovae or spiral rotation rate or something like that to try to measure this. And some of these are better measures than others, and that's why you'll see different distance measurements for the same galaxy cluster. They don't all agree always, and that's why you'll see different velocity measurements too. Is that sometimes you'll measure, there's a lot of noise in this data, it's a hard measurement to make, and sometimes you'll measure a different velocity that way. So then what we would have gone on to do in our work in lab would have been to measure the Doppler shift on the spectra of some galaxies. So some galaxy clusters, and we were going to measure these Doppler shifts by measuring these dark lines moving across. You see the dark line right there moving across this spectrum, and get delta lambda and divide by the lambda of the dark lines down in here. And we were going to find the dispersion of this spectrum, just like we found the dispersion of the spectrum in the Earth and Arcturus lab, and move on. But what we'll do here today is look at an example of this and say, let's look at an example from this data table right here. Let's take Pegasus 2. So Pegasus 2 in this data table says that the distance is 225 megaparsecs. So if the distance is 225 megaparsecs, is equal to the velocity of recession, and it says the velocity of recession is 14,850 kilometers per second. So we have 14,850 kilometers per second divided by h naught. Let's see what that gives us for a Hubble constant. We move it up, we move that down, a little swippy swappy. We say h naught is equal to 14,850 kilometers per second divided by 225 megaparsecs is equal to, trusty calculator here, we've got, trusty calculator isn't so trusty, there it is, 14,850 divided by 225 is equal to 66. So we have 66.0 kilometers per second per megaparsec. So sort of right in that range of what we were talking about. Some measurements give us 67, some give us 74. Any single measurement is going to have some noise and scatter around it. We get that 66.0. Let's take our measurement. Let's take our 70 kilometers per second per megaparsec and do a calculation the other way. let's say, let's pick the Gemini cluster here. So the Gemini cluster in our data table says that it's receding at 27,140. Let's look at Leo. It's only got one measurement. So Leo is receding at 22,300 kilometers per second. So this is the way we more likely would use it, is to say the distance is equal to 22,300 kilometers per second divided by 70 kilometers per second per megaparsec. Kilometers per second cancels out. 1 over megaparsecs is going to give us an answer in megaparsecs, and let's try it. So let's see what we have right there. We've got 22,300 divided by 70 is equal to 319 megaparsecs. We probably only know 2 digits there. That's 70. That's a fuzzy number, right? So let's only keep 2 digits there. Let's call that 320 megaparsecs would be our distance. So we've got 320 megaparsecs. What did we have in that measurement that was made of the Leo cluster? 310. So again, there's going to be noise in any one measurement, but we would do that if we just used our best guess at the Hubble constant and measured the recession velocity for this one cluster of galaxies, we would get a distance of 320 megaparsecs. So you're going to have a handful of these to do in your homework for Monday. And so take a look at this Hubble Law. Hubble Law, linear relationship between the speed of recession and the distance of the galaxy. So you can do this kind of stuff. Let me know if you have any questions about it. Slide 11 in your PowerPoint is about rotation curves of spiral galaxies. And I think we're going to skip that by and large for now. So slide 11 in your PowerPoint slide talks about these rotation curves and leads to this idea of dark matter. One of the first pieces of evidence for dark matter. We will talk about that Monday or maybe a little bit on Wednesday. It'll be one of the last topics that we cover in class. So we'll circle back to that and more or less skip that for now. Thanks, everybody. Have a good day.